Hello everyone, I am Matsuura. I am glad to have a chance to talk to you. Now, wireless power transfer systems having multiple transmitters suffer from magnetic interference, so I would like to talk about the solution to this problem. Now, let me begin my presentation. Recently, resonant inductive coupling wireless power transfer has attracted attention. This figure shows the basic configuration. The inverter feeds an AC voltage to the resonator, which generates an AC magnetic field. The receiver receives power via the magnetic field. As an expected application, there is a wireless charging desk as shown in this figure. The desk can charge multiple receivers, such as a light and a PC, on a large area. To realize a large area big WPT system, arraying multiple transmitters can be an effective method. In this case, it is desirable that each transmitter generates a stable large magnetic field. This is because transmitters can deliver sufficient power. Besides, the magnetic field by transmitters must not exceed a limitation. However, the transmitter driven by a constant voltage does not satisfy this performance. Realistically, according to the required power, the load condition is variated. Consequently, the transmitter current amplitude fluctuates. Then, the magnetic field also fluctuates. Therefore, this performance can be satisfied by controlling the transmitter current amplitude to be constant. One of the methods to control the transmitter current amplitude to be constant is to control the output voltage of the inverter. As a regulation method, a phase shift full bridge inverter is widely used. In this method, each gate signal is set to a 50% duty cycle. For example, when VG3 is shifted by delta from VG1, the output voltage of the inverter VS can be controlled as shown in this waveform. Hence, by detecting the current amplitude and adjusting delta optimally, the constant transmitter current amplitude is achieved. Then, by applying inverter to each transmitter, the system can generate a stable magnetic field. However, there are two factors that hinder the practical application of this system. The first factor is the load variations. These are the transmitter current, the output voltage of the inverter in transmitter 1, and the operating waveforms. For example, assume that in a heavy load condition such as a large power transmission, the operating waveforms are shown in this figure. In this case, I1 lags behind the rising edge of BS1, which results in achieving zero voltage switching or ZVS. However, when in a light load condition such as small power transmission, I1 leads against the rising edge of BS1, which results in hard switching. Therefore, the load variation can cause the hard switching, which results in increasing the switching losses. The second factor is the cross interference among transmitters. The induced voltage by the magnetic coupling among transmitters has a negative influence on the system. For example, we assume that the worst case is occurred in transmitter 1. This induced voltage can be divided into two components. The first is the identical component to I1. This component causes to exchange effective power among transmitters. As a result, an inverter with larger power capability is required, which results in increasing in size and cost. The second is the orthogonal component to I1. This component causes to change the current phase, which resulting in causing the hard switching. Therefore, the cross interference has both negative influences on the system. Therefore, the purpose of this study is to propose a transmitter with a constant current amplitude control that has the following performances. The first is to realize the ZVS operation regardless of the load condition and the cross interference. The second is to prevent transmitters from exchanging effective power with one another. As the approach to realize this transmitter, at first, I will show the required condition of the transmitter that has the objective performances. Next, I will establish the control strategy to satisfy the required condition, and finally, propose a method to realize the control strategy. I will show the required condition of the transmitter. First, to realize the ZVS continuously, regardless of the load condition and the cross interference, it is required that I1 lags behind the rising edge of PS1. Next, to prevent exchanging effective power between transmitters, it is required that induced voltage that is identical to I1 is eliminated. In other words, the induced voltage by transmitter 2 VT must be orthogonal to I1 as shown in this figure. If we define the operating angular frequency of each inverter as omega and the mutual inductance as M12, Vt can be expressed by this equation. So to satisfy this orthogonal relationship, each transmitter current must be in phase. Based on the requirement, I will show the control strategy. As an example, assume that transmitter 1 is a heavy load such as a short distance between transmitter 1 and receiver. Transmitter 2 is a light load such as a long distance between transmitter 2 and receiver, and there is magnetic coupling between transmitters. Even in this condition, by inserting a variable reactance to each transmitter, each current phase is controlled to its operating waveforms as shown in this figure. To realize the performance, first, the variable reactance controls the current phase to maintain the phase difference between each current and the rising edge of each inverter's output voltage as a constant value alpha. In addition to this, by setting the rising edge of each inverter's output voltage to be identical to make each current to be in phase. These are the control strategy, but variable reactance components mostly require complex systems to control the current phase as desired, as shown in this figure. In this study, we apply a simple switching circuit called attack as a variable reactance. The attack was originally proposed to adjust the resonant frequency of the transmitter resonator. However, by using its operating principle, the attack can control the current phase as desired without complexity. Therefore, we use attack as a variable reactance to control the current phase as desired. Next, I will show the operating principle. These are the configuration of the transmitter with the attack, the output voltage of the inverter, the transmitter current, the output voltage of the attack, and the operating waveforms in steady state. The attack consists of the half-bridge circuit and the smoothing capacitor. The DC voltage is generated automatically at the capacitor because of the charge or discharge by IP. so an external power supply is not required. As shown in this figure, the attack is driven by the same operating frequency as the inverter and is fixed at a 50% duty cycle. In addition to this, by shifting the phase of dA from the rising edge of ds1 by pi over 2 plus alpha, the current can be controlled as this figure. This is because the attack ideally has no resistive component due to its configuration and does not generate effective power in steady state. So, IT should be orthogonal to dA. Therefore, it can be seen from the waveforms of the PS and IT. By presetting the phase of dA, the attack can control the current phase to maintain alpha. Summarizing above, I showed overview of the proposed transmitter. As an example, assume that transmitter 1 is a heavy load, transmitter 2 is a light load, and there is magnetic coupling between transmitters. Even in this condition, the transmitter current amplitude is controlled to be constant by using the phase shift full bridge inverter. Furthermore, by the control of the current phase using G circuits, each transmitter current is controlled so that the phase difference is alpha, which achieves the ZVS continuously. In addition to this, by driving each inverter by same signal, the rising edge of each inverter's output voltage is set to be identical. As a result, each current is controlled to be in phase, which prevents exchanging effective power between transmitters. Therefore, the proposed transmitter realizes the objective performance. Then, we carried out experiments to verify the effectiveness of the proposed transmitter. There are two purposes. The first is to verify the ZVS in different load conditions. The second is to verify the compensation of the cross interference among transmitters. This is the experimental setup, and the receiver coil was placed on two transmitter coils. Then, this is the system configuration and tagged parameters. Each transmitter resonator was designed to be slightly inductive. Although the operating frequency of the proposed transmitter is not limited, each inverter was driven at 100 kHz for simplicity. These are transmitters to be compared. One is the conventional transmitter that has a constant current amplitude by the phase shift full bridge inverter. The other is the proposed transmitter that has proposed current phase control additionally. First, I will show the experimental results to verify the ZVS operation in different load conditions. This experiment was carried out by this system with transmitter 1 and receiver without driving transmitter 2. These are the output voltage of the inverter, the transmitter current, the output voltage of the attack, the receiver current, and the load resistance. Besides, IR is set to be 1.70 ampere and 1.06 ampere by adjusting RL for the verification under different load conditions. These figures are the experimental waveforms in the conventional transmitter and proposed transmitter. In the conventional transmitter, the inverter operates under the hard switching condition in both load conditions. Besides, the phase difference between the rising edge of ES1 and I1 is changed. However, in the proposed transmitter, I1 is orthogonal to BA1. and the phase difference between the rising edge of PS1 and I1 is constant in both load conditions. Therefore, the proposed transmitter achieves the ZVS even in the defined dots. Next, I will show the experimental results to verify the compensation of the cross-interference among the transmitters. These are the output voltage of the inverter and the transmitter current. Besides, IR is set to be 1.06 ampere to verify the effectiveness against the cross-interference. These figures are the experimental waveforms in the conventional transmitter and the proposed transmitter. In the conventional transmitter, due to the cross-interference, each current phase fluctuates. Furthermore, in this experimental condition, each inverter operates under the hard switching condition. However, in the proposed transmitter, each inverter achieves the ZVS and each current is controlled to be in phase. Therefore, the proposed transmitter can compensate for the cross-interference among transmitters. Finally, I would like to summarize this study. In this study, we propose a transmitter to realize this purpose. In the experimental verification, the proposed transmitter can achieve the ZVS regardless of the load conditions and compensate for the cross-interference among transmitters. In conclusion, the proposed transmitter is promising to realize a large area dipped WPT system that is not affected by the cross-interference among transmitters. Thank you for your attention.